In this lecture, we want to prove this result. So say you have a Galois extension, E over F. So this is Galois if and only if it is normal and separable. So in this direction, we have already proved this. This was proved in the lecture on automorphisms of splitting fields. So we have to prove in this direction. So we are given a Galois extension, and say we are given a group, which is the group of automorphisms for the Galois extension which fix F. So automorphisms of E which fix F. So this you set as G. So this F is nothing but E superscript G. So precisely the field which is fixed by this group G. So this group G consists of these automorphisms, identity map which says phi1 then phi2 all the way to phi n. So this is just the setup of this problem. We are just trying to unravel this statement E over F is Galois. So to prove that it is normal and separable, what we want is, we want a polynomial px in f, that is polynomial p over f, and we will say that one of the roots, so one root of this polynomial p, this lies in our field E. So then this p would split completely over E. So p, we have to show this splits completely over E. So splitting completely over E means that E is normal, and then we have to also show that P is separable. So that is, it has distinct roots. So we have to show that P has distinct roots, so it is separable. So this is what we need to show. So we have to say that, okay, one root of P lies in E, and then show all other roots lie in E, and then show that roots are distinct. That's how we will show normal and separable. So we start with the irreducible polynomial P over F and say one root of this irreducible polynomial, this lies in E. So this is the root of our irreducible polynomial. So this group G, this acts on A, our root A. So acts on A means you have A and then phi 2A. So phi 1 acts on A, gives you A, then phi 2A, phi 3A, all the way to phi n A. So you have these n elements here, but out of these n elements, maybe there are less number of distinct elements. Maybe all of them are distinct, maybe lesser than them are distinct, but you just choose distinct elements. So you just distinct elements you choose are A, A2 all the way to AR. So say var phi is another element of a group G. So var phi is one of these automorphisms. We could have written phi j also, but we are just writing some var phi's in G. Then you multiply this var phi with this group here, then you're just permuting the elements of the group. You know, this group is closed, so you put var phi here, you're just permuting the elements. So you have var phi to everything. You again get the group G. So only the elements have been permuted. So if you take this var phi and you apply here again, you're not going to do much. You're just going to permute them. So you're still going to get these distinct elements A to AR. So applying var phi will still give you A to AR. So it's simply permuting the elements. Now, so what have we done? We started with the root A, and to this root A we have applied these elements of the group. So you get this. So this is simply permuting the elements. So from this we construct a new polynomial f of x which has these roots, so x minus a, x minus a2, x minus a3 all the way to x minus ar. So our life is very simple if we can show that this is equal to p of x, because obviously then you can see this p of x has splits completely over E. All of these elements a, a2, a3, ar lie in E. After all, you know, this these phi's are nothing but automorphisms of E. So they act on some A, they will put them back in E. So it splits completely over E, and you can see it is separable. It has these distinct roots A, A2 all the way to AR. So what we want to show is that this simple polynomial f we have constructed is equal to p of x, and that will be the end of the proof. So the strategy we are going to follow is this. So first we will show is that p divides f, and then we will show that f divides p, and therefore f would be equal to p. So let us do this statement first. Now, since elements of G simply permute the distinct roots here, leaving the coefficients fixed. So if G acts on this, it's just going to change these elements a to a, are just going to permute them. X is not going to get changed. So therefore, if you expand this polynomial, the coefficients are fixed, only the roots are changing. So f lies over this field f. Now, since px is a minimal polynomial with root a, so you can use the division algorithm. So you divide throughout like this. This is what you get. Now you plug in a. So if a is the root of x also, you can see it right here. So this will become 0, and this will be qa, pa, and then ra. So pa is also 0. So this would imply that ra is 0. But r is a remainder by division algorithm, and degree of r is less than degree of p. So this would violate the minimality of p. So it has to be the case that this remainder does not exist, because if this remainder exists, then you have found a minimal polynomial r of x which has root a. But we are saying p of x is a minimal polynomial. So it has to be the case that this r of x is 0 and this p of x divides f of x. So in the lecture on automorphisms, so we had a lecture on automorphisms, we showed that if a polynomial has some root a, then it will also have this root phi of a, where phi is automorphisms of e which keep f fixed. So which is precisely here, the automorphisms of e which keep f fixed. So if a polynomial has a as a root, it will also have phi of a as a root. So what are these possible values of phi of a? We have seen possible values of phi of a is a2 all the way to ar. So we already know that our irreducible polynomial p has a as a root. So therefore it will also have phi of a as a root. So our irreducible polynomial, this irreducible polynomial, will have all these as a root. So since it has all these as a root, it could have multiple roots. And the simplest form it can take is this. So the f of x has all these roots. So f of x has to divide p of x, because p of x now we say could have multiple roots because it has to have all these roots. So we have shown that now f divides p, p divides f, f divides p. So f of x has to be equal to p of x, and you can see that p of x is separable. It has distinct roots. Now we want to go further. We also want to show that this e is splitting field for some separable polynomial g over field of f. So since we are saying a splitting field, not only we have to show that g splits in this field, but we also have to say that this field is the minimal possible. So the first step is to construct this polynomial g so that it splits easily. So say you have b1, b2 all the way to bn. This is the basis of e over f. So corresponding to each of these basis elements, you can construct minimal polynomials. So corresponding to b1, you have minimal polynomial p1. Corresponding to b2, you have minimal polynomial p2. So corresponding to bi, we have minimal polynomial pi. Now each of these pi is separable. We have just shown it right here, and it has all its roots in e. So this is what we showed above. So now you set g of x is product of all these n minimal polynomials, and you remove any multiple factors. So removing multiple factors makes g a separable polynomial. So then g becomes a separable polynomial. So now we have constructed a separable polynomial, and e is its splitting field because each of these polynomials splits. It is separable because we have removed multiple factors, and e is the splitting field precisely because the only things we have adjoined to f are these basis elements b1, b2 all the way to bn, and all these basis elements correspond to minimal polynomials. So e is just constructed by adjoining roots of these minimal polynomials. So therefore it is a splitting field for some separable polynomial. So we have now shown that e over f is Galois, then e is the splitting field for some separable polynomial. So before we end this lecture, let us give another definition. So say var phi sits in this group of automorphisms of E which fix F, and we are writing it as Galois because E over F is a Galois extension. So this var phi will act on some element A in E precisely in this manner. So we are trying to construct a definition. So A in E, and this A corresponds to these elements under action of group G. So these will act on A like this. So these elements phi of A, which are precisely like these elements here, these are called Galois conjugates of A over F. So you just all these are Galois conjugates of A. So just apply G to A and see where G sends A, and wherever it sends it, those are the Galois conjugates of A.